Okay, let's do problem number 31 on page 212. It's on chapter 7. I'll read the problem out loud. It says, a 40 kilogram box is initially at rest and it's pushed 5 meters along a rough horizontal floor with a constant applied horizontal force of 130 newtons. If the coefficient of friction between the box and the floor is 0.3, find A, the work done by the applied force, B, the increase in internal energy in the box floor system due to friction, and C, the work done by the normal force, D, the work done by the gravitational force, E, the change in kinetic energy of the box, and F, the final speed of the box. Okay, so there's a lot to find here, although some of these are going to be really quick. So let's solve this. So I want to know how much work was done by the applied force. Well, I'm going to start here. Okay, this will be silly, but work equals the integral of F dot ds. ds is the path, and F is the force that's being that we're looking at. This is the general formula for work. So now I'm going to take this and I'm going to apply it to this situation. The work done by the applied force. Well, the work done by the applied force is just a constant 130 newtons. So it comes out of the integral. And so you have 130 newtons. And the sum of ds, well, that's just the total displacement, delta x. And delta x here is 5 meters. And then the dot product means you have to multiply by the cosine of the angle between the force and the displacement, but they are parallel. The force and the displacement are both in the horizontal direction, so the angle between them is 0. The cosine of 0 is just 1. And so the work done is just 130 times 5. So here's 130 times 5 equals 650. A newton times a meter is a joule. Okay, so that's pretty easy. Now, for part B, the internal energy added to the environment, okay, by friction. Well, that's the work done by friction. I mean, as this thing scoots along the horizontal floor, friction is heating up the environment. And that's turning the energy of the system into internal energy, or just the random motion of molecules, and the energy is just being dispersed in the environment. We call that internal energy. So we need to find the work done by friction. That's really what it's asking. And the work done by friction is, again, using this, friction times delta x, which is 5 meters. Now the angle between the force of friction and the force of friction is going to be, to the left. And maybe I should just draw a quick little free body diagram, because that will come in handy for the other problems. Here's a normal force. Here's mg. Here's the applied force. And here's the force of friction. And so, well, the force of friction is mu times the normal force. So mu times the normal force. But what is the normal force equal to? Well, the normal force, if you look in the y direction, the normal force is just supporting the weight. I mean, you can go ahead and go, okay, the sum of the forces in the y direction equals ma in the y direction, but in this problem there's no acceleration in the y direction. So you have the normal force minus mg equals 0. So n equals mg. Force of friction equals mu times the normal force, so that's mu mg times delta x. I'll just go leave it in variable form there. And so mu is given to be 0.3. The mass was given to be 40 kilograms. G on Earth is 9.8 newtons of force for every kilogram of mass. Delta x is given to be 5 meters. And now, the angle between the force and the displacement is 180 degrees. So this is going to be cosine of 180 is -1. So let's do this. So 0.3 times 40 times 9.8 times 5 is 588. Well, negative 588 joules is the work done by friction, but all of this energy, the energy lost by my system just gets dispersed in the environment. So we can say that we added 588 joules of internal energy into the environment. Okay? Hopefully that makes sense. All right, let's do part C. Well, look, I'm not going to spend too much time on it. Look at the normal force. The normal force is up. The displacement is to the right. The angle between the force and the displacement and the normal force is 90 degrees. So when you take the dot product of the normal force and the displacement, you get 0. Because the angle between them is 90 degrees, the cosine of 90 is 0. 0 work. So I'll just put, like, the normal force is like this, delta x is like that. And of course, by the same reasoning, gravity is straight down and the displacement is horizontal. So again, it's a 90-degree angle, 0 work done. Here's mg, and here's delta x again. Oops, off screen. Tell me if I'm off screen, guys. No, don't say, just shout.
Okay.
That was Dimple. She wanted me to do this problem. All right, now. Okay. Now, the last one, well, no, it's not the last one. Let's do E, the change in kinetic energy. Well, I'm going to use the work energy theorem. That is, the work done by the net force is equal to the change in kinetic energy. Well, what is the net force? Well, it's the applied force. Look in the x direction here. The net force is the applied force minus the force of friction. That's the net force times my displacement, delta x. Okay, and the net force is to the right, and our displacement is to the right. So we're going to have positive work done. And the applied force is 130 newtons minus my force of friction. Did I even calculate that? Well, I put it in the calculations. Mu times the normal force, so that's 0.3 times 40 kilograms times 9.8 newtons per kilogram. So that's 117.6 times delta x, which is 5 meters. So my net force is 130 minus 117.6. That's 12.4 times 5, and we get 62 joules. So we increase the kinetic energy by 62 joules. Now there's another way of doing this, and that is, look at this. The net work, the work done by the net force is the same as the net work done. The work done by my applied force was 650 joules. But the work done by the force of friction is 588 joules, negative 588 joules. So if I add the work done by my applied force plus the work done by my force of friction, I get 650 minus 588, and that is equal to 62 joules. It all works. All right. And for part F, well, delta K, we want to know the final velocity. So delta K equals K final minus K initial. Well, K initial is 0 because it says it's at rest. That was given to be at rest. So that's equal to 1/2 mv squared. So the final velocity is going to be 2 times 62 joules. My delta K is 62 joules, divided by the mass, which is 40 kilograms. And then I got to take the square root, or just the 1/2 power will work. And so you get 62 times 2 divided by 40. You get 3.1. And then you have to take square root of that. And I get 1.76. And a joule divided by a kilogram. A joule is a kilogram meter squared per second squared. Cancels out the kilogram, you get meters squared per second squared. Take the square root of that, you get meters per second. And there you go. All done. Let's take a look at the whole thing all together. I really think it's cool that you can figure out what the net force is and multiply that by the displacement and get the change in kinetic energy. Or you can look at the work done by each force, 0 plus 0 plus 650 plus negative 588, and get the same answer. That is the net work done. That is all.